Good morning, students. In this video, I am going to explain spatial filtering operations in the image enhancement techniques. So, of course, you know that in the image enhancement, we have the two different techniques: spatial domain techniques, frequency domain techniques. Under spatial domain techniques, again, we have the two different operations. One is the point operation, another one is the spatial filtering operation. Otherwise, it is also called as neighborhood operations. Here we have completed point operations. Now, the topic is spatial filtering operations. The type of operation performed in the neighboring input pixels is called as spatial filter or spatial mask or kernel or template or window or neighborhood operation. So this is the definition for the spatial filtering operation. So that means here in the point operation, the particular operation is applied on input pixel value and corresponding pixel value is changed in the output. That means that should be satisfying the what is that the relation S is equal to T of R. That means here if we just apply the particular operation on the x comma y, that means the location, then we will get the changed value at that same location. So here that is said to be point to point operation, right? Now here a spatial filtering operation or neighborhood operation is nothing but, so here we just apply the certain operation in the particular location for the input image, but that operation is involving in the neighbor pixels of the particular location x comma y. Then you can get the modified value for the output image at the location x comma y, right? So here the number of neighbor pixels of the x comma y depends on the mask size or kernel size, template size. Okay, now here that's why here the definition for the spatial filtering operation is the type of operation performed in the neighboring input pixel values is called as spatial filter or spatial mask or kernel or template or window or neighborhood operations. These are the another names. It consists of moving the origin of the neighborhood from pixel to pixel and applying the operator T to the pixels in the neighborhood to yield the output at that location. Thus, for any specific location x comma y, the value of the output image g at those coordinates is equal to the result of applying the transformation operation T to the neighborhood with origin at x comma y in F. Right? Now, so here the spatial marks, another names, kernels, templates, windows, we have seen, right? Now, so it consists of, the spatial filtering operation consists of mainly 2 points. What is that? Developing the particular window or developing the kernel or developing the mask, right? So here it consists of a neighborhood, okay, or a neighborhood or mask. And the second one is a predefined operation that is performed on the image pixels encompassed by the neighborhood. So here the spatial filtering operation is involving mainly two things. What is that? The first one is developing a mask or neighborhood. That means, so we have the different sizes and different shapes. So we should develop the shape like square, what is that? Rectangle, any circular with some radius like that. We should first develop the that means according to the application. So we should consider the one shape, right? Usually we are using the square marks. Okay. Now, and also size. According to application, which size is here important, right? That means, so we may consider, for example, in square marks, 3 by 3 marks, like 5 by 5 marks, like 7 by 7, like that. So to identify the center pixel, what is that? Comfortably, so we should select the different sizes. Okay, so that means usually we may consider 3 by 3 like that. Okay, so now here along with this particular mask, what is that development, after finding the mask, after choosing the mask, then we can immediately determine the operation, right? Which operation we should perform by using this mask on the input image. That is the important here. Okay, right. So here filtering creates a new pixel with coordinates equal to the center of the neighborhood, right? So that means here filtering means here that develops a particular new pixel value. What is that here? Those are having the coordinates, right? So that is equal to center of the mask. Okay, right. That means here, here we may apply different operations. So here if that operation is linear, then such filter is said to be linear spatial filter. Otherwise, it is said to be non-linear filter. Okay, so that means here we have the two different things. One is the linear spatial filtering operations. Another one is the non-linear spatial filtering operations. So now here this is the mechanics of spatial filtering. Okay, so here you just consider 3 by 3 mask, right? So this is the 3 by 3 mask, right? So square mask and size is 3 by 3. How many filter coefficients are there, or mask coefficients are there, or weights are there? 9. Okay, so right, you should first develop the filter coefficients according to this mask. Like this is, if it is nothing but a center pixel, so that is which is coincident with the here x comma y. So that is here we should modify the particular pixel value. So here you should coincident or what is that fastening here this mask to meet the x comma y to this center pixel. Okay, it's okay. Now here that is said to be here w of 0 comma 0 or w of x comma y. Okay, right. So now this is nothing but w 0 comma 1 or x comma y plus 1. Here this is w of 0 comma minus 1 or x comma y minus 1. Okay, right? Like that. Here, so you know that neighbor pixels of the x comma y or 0 comma 0. So from that idea, you just develop the different weights or filter coefficients first, right? According to the operation. Okay, right here. Then this mask is placing in the input image at each location, and after applying the operation, this mask is right moving from particular location to the another location, right? So here this mask is moving here throughout the input image. Okay, which here that means to complete the all the pixel values. Okay, now here if I take here w of x comma y, so it is coincident with the f of x comma y, for example f of x comma y, and now here this covers the neighbor pixels of the input image pixels like this one. Okay, right. That means f of x comma y plus 1, f of x comma y minus 1, and so on, like this. Okay, so see here. So that means here it covers the 8 neighbors of f of x comma y. Okay, right. Then according to the operation, we should develop the coefficient values. So these values, right? So are are performing the particular, what is that, operation on this image, then on this particular pixels, right? So in the input image, then you can get the modified value, that is nothing but f of x comma y modified value at this position. F of x comma y, if you have one value at the input image, so by finding the value, new value based on these weighted coefficients and based on these neighbor pixels of f of x comma y, you can get the modified value, and it is stored in, what is that, g of x comma y. So let it be g of x comma y is the enhanced image or output image. Okay, right. Now if I place this filter coefficients to the next value of the x comma y location, so here that is nothing but this one. So that means now the center pixel of this mask is coincident with this, and then here at this position consider the 8 neighbor pixels. 8 neighbor pixels. That means from f of x minus 1 comma y to the here f of x plus 2 comma y plus 2, like that. Consider the 8 neighbor pixels of the f of x comma y plus 1 and perform the operation, and then the modified value is stored in f of g of x comma y plus 1. Okay, like that. So here the mask is placed in the input image, and then do the operation, and then change the value at the center pixel of the particular mask for according to the input image, and that mask is continuously moving. Okay, right? So to change the value at each location. That means here this operation is almost, that means related to some input value is there, some system operation is there, you can get the output. That means output is nothing but, right? So in the spatial domain, input which is convolved with the system. We know that. That means if you take some analogy between this image with the signal, so here the output is nothing but the input convolved with system. Here also you perform the certain operations in the convolution. What is that? Shifting, folding, shifting, multiplication, summation, like that. Here also this particular, to get the output image, so here also we perform different operations, right? So here developing this mask like a system, and system is placing on the particular image means, so here that is multiplying, that may we may use different operations, multiplications, additions, and also shifting of the mask. So that's why here also we just use the word, what is that, convolving. Convolution between this mask and input image will give you the enhanced image. That means you may use the here convolution or correlation. Of course, but obviously you can get the, what is that, output image. Okay, right. Here basically we should know the operations like convolution and correlation, but in our syllabus we do not have that topic, but remember that. So here from this particular what is that, neighborhood operations or spatial filtering operations, so okay, you can notice that, what is that, so here convolution operation is involving. Okay, right, it's okay. Now here coming to the spatial filtering. Spatial filtering already told, so is a filtering operation that is performed directly on the pixels of an image. The process consists simply of moving the filter mask from point to point in an image, right? So here under this spatial filtering operation, right, again we have the segregation, right. So here we have the two different types of spatial filtering operation. One is the smoothing, another one is the sharpening. Smoothing spatial filters, sharpening spatial filters means if you consider the input image, consider one input image. So if you want to do the smoothing the particular image, right? Okay. So here we should apply smoothing spatial filtering techniques. So this is nothing but here low pass filtering action. Here low pass filtering action. Coming to the next one, if you want to sharpen the particular input image, we should perform sharpening spatial filtering techniques. That means it is the high pass filtering operations. Okay, remember that smoothing spatial filters are related to low pass filtering operations. Sharpening spatial filters are related to high pass filtering operations. Now here, coming to the word, what is that? Filtering, right? So filter means, you know that, what is the filter? Filter means which removes the unwanted frequency components and allows only the desired frequency components. You know that particular filter definition. Here also we are using that word. What is that? Spatial filtering. So here what is that? What is the filter? Filter means here the intention is the same thing. What is that? Which removes the undesired frequency components and allows only the desired frequency components. Yes, here also we should use the word. What is that? Frequency. That's why I just here what is that? Added low pass filtering action, that is related to the smoothing, and high pass filtering action, that is related to the sharpening. Okay, so here coming to this one. So how can you take a particular similarity, that means in between the frequency and the image? Here observe, take one image, right? So here image means it has so many pixels, so many intensity values, right? So intensity values are placing like what is that? If you observe row wise, either row wise or column wise. That means here you may expect like that. What is that? 10, 9, 10, 10, 10, 10 like that. And then 10, next 0, next one is the 1, 2, 3 like that. That means here if you observe the particular what is that, pixel intensity values either in row form or in column form. So here the values are here, right? So that means what is the change in the particular values. So right, how these values are varied, right? That means 5, 5, 5, 5, 5 means it's a constant variation, right? 5, 10, 100 like that. That means 10 to 100 means abrupt variation, sudden variation, right? Am I correct? 1, 2, 3, 4, 5 like that. So now that is linear operation like that. So you just, if you consider the particular, if you analyze the particular image, right? So here you can easily say that, so what is the variation here, right? In between the pixel intensities. Okay, you can get the particular what is that idea here. Okay, right. That means here according to that you may what is that relate this image with the frequency. So that means what is the frequency? Actually rate of change. So it is also nothing but it is the inverse of the period, right? So that means amount of time it takes to cycle from one brightness to a different brightness and back again. So I am applying this particular definition to the image. Okay, to the image. That means you know the general definition for the time period and frequency. So here observe what is the frequency, rate of change. Am I correct? What is the time period, that is the particular frequency is inversely proportional to the time period, and then what is the time period actually? The particular wave to complete one full cycle, right? So how much time it takes, right? That is nothing but time period. Am I correct? Here in particular for an image, here period is nothing but, can I say like this? What is that? The amount of time it takes to cycle from one brightness to a different brightness and back again. Okay, right. So here the faster then change, right, the higher the usual frequency required to represent that part of the image. Right? So in other words, you can think of frequency in an image as the rate of change. Parts of the image that change rapidly from one color to another. Parts of the image that change rapidly from one color to another that contain high frequency. And parts that change gradually that contains only low frequency. Observe these two here. What is the here general meaning here? Tell me. High frequency, low frequency. Consider these two levels. Okay. Frequency is rate of change. So okay, here what do you mean by high frequency for in the image? What do you mean the high frequency? What is it for an image? High frequency means, so here high rate of change, right? High rate of change means, sir, there is a pixel intensities. So the difference between those successive pixel intensities should be, right, so very large, very high. So that means here the pixel intensity value is changed, right, rapidly, abruptly. That means at one location the value is 100, but in next location if the value is like a 0, right, that means here 100 to 0 variation means very large. So that's why here you can say that here the particular intensity variations are so in the form like high frequency. Right? Okay. That means observe if particular intensity is 100 at one place, another place 0, it looks like a one edge. Am I correct? Sudden color variation looks like a edge. Okay. Right? So here that means here high frequency, that word is related to the edges of the particular object in the image. Okay. Particular object in the image. So that resembles, high frequency resembles the sharp edge or simply edge. Okay, remember that. Okay, that means here the next one is low frequency. Low frequency means rate of change is low. Rate of change is low means here the variation in the intensities is low. That means like 555 or 543 or 541 like that. That means here what is that? The change is 10-5 like that. That one also somewhat low, right? Like that. If the variation is, right, it's almost same or very low. Almost same means 10-10-10 like that. 100-100-100 like that. 250-250-250 like that. So very low. Very low means 250, 251, 252 like that. Otherwise 250, 255, 260, 262 like that. That means here variation is the same or variation is low. That is related to the low frequency. Then if you observe in such a case, the particular variation in pixel intensity variation is similar or low. So that is nothing but here, what is that? Surface of the image. Am I correct? Surface of the particular object in the image. So here that means here edges word is related to the high frequency, and then particular region or surface of the object word is related to the low frequency. Okay, so here also observe high frequency means time period low, and so rate of change is high. Here low frequency means time period is high, rate of change is low. Okay, right. So remember these two particular figures in our mind. Okay, so what is the high frequency and what is the low frequency for an image, right? So then here you can easily understand the smoothing operation and sharpening operation if you understand this particular low frequency, high frequency for an image. Okay, right. So now here tell me. Now what is here low pass filter? Low pass filter means which allows, that filter which allows only low frequencies and attenuates high frequencies. Am I correct? That means in an image, in an image. So what is our expectation? So low frequency, it allows only low frequencies means, so here small variations in the intensities. Okay, so it should be okay, right? So but we should concentrate on the high frequencies. High frequencies means sudden variations. That means you should eliminate those sudden variations in the particular image. Okay, observe. That means that eliminates the, what is that? Edges, or reduces the edges. That means sudden variation intensities. That means 100 or 10 pixel intensities are there. That means here the large variation is there in the intensity. That is nothing but high frequency nature. That means if you apply the low pass filtering operation on the particular image, if the particular values are there like this, high frequency values, that means high intensity variations, 100, 0, like 110, 150, like the 255, 50, like that, then what we can do? So you could not eliminate those values, but we just here, right? So reducing that effect here. That means, so here 110 means 100 value is reduced, 10 value is increased. Okay, 100 value is reduced to the maybe 50, 10 value is increased to the maybe value 40. Now 110 will be changed like, what is that? 50, 40. Now what is the case here? Edges slowly, right? Edges or high frequency values are changing slowly and converted to the low frequencies. That means small intensity variations, like that. So that means low pass filtering operation means, or smoothing operation means. So here high transitions, sudden transitions should be, right? So reduced. Okay, so values are, we just concentrate on these edges. We just apply this low pass filtering operation on the particular image. Then you can reduce that effect, what is that? Edges effect, right? So and then here that is nothing but smoothing. Okay, right. Now coming to this one, high pass filter. What is that? Sharpening. What is the high pass filter? General meaning. So it allows only the high frequencies and removes the low frequencies. That means here allows only the low frequencies means, that means in particular for an image, if you observe, so that means here small variations of particular intensities are, that effect is reduced here. Okay, so here in the same way as in a low pass filter, right, here you should concentrate on small variations and then those values are here increased, okay, according to this high pass filtering action. So that means here maybe edges also, right? So sharpen. That means if you have the 10, 20 like that. So if you apply the high pass filtering action, which improves this value like 10 to 0, 20 to 40. Like here 10, 20 values are changed to 0 to 40. That means you just sharpen the edge. Sharpen the edge. It is called as, what is that? Sharpening. Okay, right. So here, remember these points here. So, okay, general discussion. So here, high frequency components, low frequency components. High frequency components correspond to edges in an image. Low frequency components correspond to regions, smooth regions. Okay, right. Or surfaces. Okay. Now, so observe this one. Low spatial frequency, high spatial frequency. So here this is the 3D graph, right? So here intensity values with respect to the spatial coordinates x comma y. So here the intensity values looks like this. See here it's a flat and somewhat small variations here, right? Here small variations. See this? So here looks like a waveform also look like this. Okay, see this. So here small variations in the corresponding small intensity variation in the corresponding pixels. So that's why that is nothing but low spatial frequency. Higher spatial frequency means sudden variations. in between successive pixels. So, right? Observe here. Right? So here, so if the particular graph is like this, right? So that is said to be higher spatial frequency, right? And then you know that here in one image we may expect the all type of frequency components in single image, right? So we may have the low frequency components and also high frequency components. Am I correct? So that means in one part we may observe low frequency, in another part we may observe high frequency, okay, in the same image. That means here observe one image, fruits image, okay. So take the same example, fruit image. Fruit image means, so here if you take the apple fruit, take only apple fruit in the image, only one single apple is there. So here that apple surface is nothing but the low frequency components. So on the surface, so you may observe the color is same, okay, right? So that is said to be same values are repeated here, the intensity values like that. That means here, here that is related to low frequency components. So when you observe the, what is that? Background and fruit picture separation. The fruit is there in particular image means some background also there and fruit is there. That means here background is separated with the fruit. Okay, that means the edge of the fruit that indicates what is that? The edge of the fruit is nothing but what is that? Sharp transition. So maybe background is along with the fruit color, you cannot separate those two. Am I correct? Right? So if you take apple is in red color. If the background also red color, right? So it is very difficult to find out the fruit, okay, in the image. Am I correct? If the background is in another color, then you can easily identify the fruit. Okay, that means in such a case, here the edge means here there is a sharp transition between the intensity values. Okay, intensity values. Okay, so that means that is said to be edge. At that position, here those are nothing but high frequency components. And also observe background. Background is if it is a similar color, right? One wall is there and then that means a similar color. So hope like that. I mean, what is that? Imagine like that. That means here that background structure also here. What is that? Related to low frequency components. That means here if you observe the image, in that image, right? So you may get the different frequency components, right? Low frequency, high frequency, of course mid frequency components also there. But here we just concentrate on like ideal case. What is that? Very low and very high, like that. Low frequency, high frequency. Okay. So okay, now coming to the first technique, smoothing. So smoothing means here, so to reduce the noise in the image, we are using the smoothing. So what is this here to reduce the noise? That means here, what is the smoothing here? Remember, low pass filtering action. Low pass filtering action means what is that? Which removes the high frequency components. Removing the high frequency components means what is that? Reduces the effect of the sharpening. What is that? Edges. What is that? Reducing the sudden transition values. Am I correct? So edges effect is reduced here. So here that means due to this, what is the advantage here? I am reducing the sudden transition values. Okay, or I am eliminating the, right? So here high frequency component values. So that means here I am reducing the sudden transition values effect here. That means edges effect. So that means here by doing this, right? So here you can reduce the noise. So particularly if the image is with certain noise, right? So here in the noise also we have the different types. Okay, certain noise. So you should want to remove that particular noise. So noise means here if you consider the one salt and pepper noise like that. So that means some dots are there. Okay, suppose. So that means here sudden transition is there. Some separate spot is there means sudden transition is there with that particular spot to the successive pixels. Am I correct? So that means that looks like a edges. So to nullify those particular sudden transitions, so here we are using this type of smoothing techniques. So and hence you can reduce the noise. Okay, that's why here what is the use of this smoothing? That is nothing but So which smoothes the image? Which smoothes the image? Don't say like that. Which smoothes the image, and what is the sharpening means? Which sharpness the image like that. Okay. Smoothing means to reduce the noise. We are using this smoothing effect. Okay. Image smoothing is a key technology of image enhancement, which can remove noise in images. So it is a necessary functional module in various image processing software. Image smoothing is a method of improving the quality of image. Am I correct? So, right? Now, smoothing is performed by spatial filters and frequency filters. That means here, in the frequency domain enhancement techniques also, we have the two different techniques. One is the smoothing and the one is the sharpening. Okay. That means smoothing is smoothing of the particular image means, so you may consider the spatial domain image or you may consider the frequency domain image. Okay. It's okay. Now, so under this smoothing spatial filters, again we have the different techniques. One is the linear and then one is the non-linear. In the linear, consider mean, Wiener, Gaussian, different types. In the non-linear, consider minimum, maximum, median. Okay. Now, smoothing spatial linear filters. Okay, these are also called as averaging filters or low pass filters. Okay, so by replacing the value of every pixel in an image by the average of the intensity values in the neighborhood defined by the filter mask. Okay, so here it is also called as low pass filter and also averaging filters. To here do the particular smoothing or reducing the noise, here we are using the averaging operation. So that's why it is also called as averaging filters. Okay. Now here nothing but what is that? Here. So we mentioned here in the linear operation. So which operation is involved? Mean operation. It's okay, right? That means the average operation. And then next one is reduced the sharp transition in intensities. Okay. Right? Am I correct? Which is reduced the what is that? Sharp transition in intensities. So random noise typically consists of sharp transition. So that's why here you should reduce this random noise by using smoothing linear filtering operations. Edges also characterized by sharp intensity transitions. So averaging filters have the undesirable side effect that they blur edges. That means here if I reduce this particular sharp transitions in the intensities, obviously you may get the particular, I mean if you are, that means if you see the image, right, here so many sharp edges are there, okay, right. So here that means we are talking only about noise, but actually some edges also there. So that desired edges also there, okay. But here after reducing this sharp transition intensities, right, so obviously, so here image is blurred. That means here values 10 to 20, 10 to 50 like that. So here you just adjust the intensities, okay. Then here by adjusting these intensities based on a certain operation, so after completing, right, this operation on the particular image, so if you observe that image, the image looks like a blur, okay, blurred image, okay. That's why here the advantage is reducing the noise, and what is the here disadvantage? Blurriness, right. So you can get the blurred image here, but after using certain techniques you should nullify this blurriness, okay, again, okay. It's okay, right, to reduce the noise. Of course, if you have the what is that blurred image, then so there are so many techniques, again you can retrieve the good image from that blurred image. So that's why here noise we just concentrate on the noise. So here based on this what is the technique, so we may reduce the noise, but you can get the blurred image, okay. Then if all coefficients are equal in filter, then it is also called a box filter. So okay, see this here, what is that, one of the mask is nothing but average filter here. So average filter mask is nothing but mask has certain coefficients. You just apply the averaging operation, then here that reduces the sharp transitions but increases the what is that blurriness, okay. And then here the filter coefficients all are equal, like 3, 3, 3, 3, 3, 3, like that, then that is said to be box filter. It's okay. Now here the other mask is called weighted average. Okay, so right, that means it is used to indicate that pixels are multiplied by different coefficients. Okay, so weighted average, that means here what is the average filter here? So in here we have the, if you take 3 by 3 mask, 3 by 3 mask, 9 coefficients are there. So here 9 coefficients are equal. Then like consider like here what is that 1 by 9, 1 by 9, 1 by 9. Okay, if I take like that, so 1 by 9. So if I apply this mask on the image, right, so here the operation is nothing but just multiplication and summation, and then the resultant one is nothing but these 9 coefficients are multiplied by the corresponding 9 input pixel values, like wx comma y is multiplied by f of x comma y, then plus they do the sum, wx comma y plus 1 is multiplied by the f of x comma y plus 1, and so on, like that. So you can get the what is that product, and what is that after completing product and sum, what is the resultant one here, f of x comma y into 1 by 9 plus f of x comma y plus 1 into 1 by 9 plus f of x minus 1 comma y minus 1 into 1 by 9. And that means each value is multiplied by the 1 by 9, since we are considering the weights are here 1 by 9. Then what is the resultant one? Common the 1 by 9, and then you can get the f of x minus 1 comma y minus 1 plus and so on, f of x comma y comma and so on, f of x plus 1 comma y plus 1, all divided by 9. That means here what is that? Averaging of the neighbor pixels of the f of x comma y. Am I correct? So f of x comma y, and then consider all the neighbor pixels and then take the average value. Right? So that means here weighted coefficients are taken like that. What is that? 1 by 9 equal values. That is said to be here box filter also, right? So in such a case, that is said to be averaging filter. That means here at f of x comma y, right? So one value is there, but the new value, new intensity value is related to the averaging value of the, what is that? F of x comma y. Averaging value means f of x comma y has the neighbors. So consider all the neighbors. That means here 8 neighbors along with f of x comma y. Do the sum here. So all the 9 values, do the sum and then divided that value with the 9. Then you can get the one new modified value. Then that is stored in the g of x comma y. Okay, right? So in such a way, just finish the right for all the input image pixel values. Okay, right? So that's why here that is said to be averaging operation. Now here nothing but weighted average means, so here weighted coefficients are not like 1 by 9, right? So here different one. That means first here wx comma y is having one value, wx comma y plus 1 is having one value. That means here f of x comma y is multiplied by the certain value plus f of x comma y plus 1 is multiplied by the certain value, right? So that means here the multiplied these pixels with the different values and do the sum and then divide the value with the 9. Okay, right? Then you can get the weighted average. Okay, so right, you may do the weighted average also. Center point is more weighted than the any other points. You may consider like that one also. That means the desired location here actually f of x comma y, so which is changed as g of x comma y. So here we can give the more weight on the particular desired value f of x comma y. So according to that you can apply the weighted average also here. So strategy behind weighing the center point the highest and then reducing value of the coefficients as a function of increasing distance from the origin is simply an attempt to reduce blurring in the smoothing process. Okay, by doing like this we can reduce the blurriness. Okay, intensity of smaller object blends with background. Okay, right? So okay, here just observe here the linear filters, smoothing linear filters. One is the weight average, another one is the weighted averaging filters. Okay, so here like this you should consider the mask. Okay, and then you should consider the mask like that. More weightage is given to the, what is that, center pixel. So and then so less effect to the, what is that, neighbors. 4 neighbors are having the less value, and then what is the diagonal neighbors are having the very much less effect. So based on this value, so here So we can reduce the blurriness, and then you just observe here, you just think here, after applying this one, how my image is. Like take just an example of any what is that image as a matrix. So and then use your own values. So that means low frequency and high frequency values are there. That means a small variation and sudden variation intensities. Just take and apply these marks, and then observe the changed input image. Okay, you can get the idea. Okay, in such a case. Okay, so now here this is an example. Okay, right, see this. Okay, so this is the one. So after applying the mask, so original image is 500 by 500. Result of smoothing with square averaging filter marks of size M, 3, 5, 9, 15, 35. Okay. So after applying 3 by 3 mask, 5 by 5, 9 by 9, 15 by 15, 35 by 35. Okay. Mask size is increasing. Okay. So now here after applying the weighted averaging mask with the different sizes. So see this. So here is small size. So effect is low. Okay, right. So if you increase the mask size, okay, so right. So see this here, sharp transitions. Observe the sharp transitions and the smooth variations. So sharp transitions are closely, right, so converted into smooth transitions. Am I correct? See this. But after getting this one, after smoothing the image, right, so here the image will be appear like, what is that? Blurred. Okay, right. It's okay, right? So here observe the values here also, right? Some values. Suppose if it is a noise, okay, right? If I apply 3 by 3 mask, that that is not much reduced here. Okay, am I correct? If you use this one, okay, this one, and this one, so see this mask size is increased. So that effect is here nullified. Am I correct? Smoothing. Okay, right? That is almost what is that merge with the background. Am I correct? So here if it is a noise, that is reduced, but what is that here result in one? Blurriness is improved. Okay, so this is the case here. Okay, now here observe here also. Okay, so right, this is one image. Another one is if I take 15 by 15 averaging mask. Okay, so I can get the image like this. Okay, after thresholding, so here see this, some of the particular things, right? So here, so the I need only this one. I don't want to this small speckles or small parts. So I should apply the 15 by what is that averaging mask, that is the size 15 by 15. See this, I can get the image like this. So here this is a blurred image, but if I use the thresholding particular operation, so here point operation, then I can get the value like this. I can get the image like this. Okay, then see this, I just concentrate on only this. Okay, right. So in this way I can enhance the image. Okay, right. So now coming to the non-linear filters. Non-linear filters means this response is based on ordering or ranking the pixels contained in the image area encompassed by the filter, and then replacing the value of the center pixel with the value determined by the ranking result. It is nothing but here in the previous case we have seen different one. What is that? Mean filter, average filter, weighted average filter, and almost we have the different filters, Gaussian filters. So many filters are there, but in our portion we have the what is that average and weighted average. That's why we concentrate on that only, and then remember here these two masks, right? These two filter coefficients, very important. And then now coming to this one, right? So here order statistics or nonlinear filters means here we just concentrate on minimum, maximum, median filters. So what is the minimum filter? You just develop filter coefficients. Okay, right? So filter coefficients means here, so here filter coefficients are 1. Okay, right? But here apply the operation. What is that? So among all the particular here input pixel, that means the pixel with the neighbor pixels. So here if I consider the 3 by 3 mask, so 9 I just choose the right f of x comma y, and along with the neighbor pixels of f of x comma y, I have the 9 pixels, right? In that 9 pixels, so I just search the minimum. So I just apply the minimum operation. What is that here? Minimum of all pixels. Here minimum of all pixels, so whatever the value, that is here placed in the f of x comma y. Okay, right? Understood? That means here at every location you should search the, you should take the neighbor pixels according to the mask size, and then among all the neighbor pixels, right? With the particular with the pixel value like f of x comma y. So do the operation, minimum operation. That means if particular value, right? So which one is a very lower intensity, that is placed in the f of x comma y. That is the minimum filter. If I take maximum operation, what is that maximum value of all the pixels, right? Pixel values, then that is placed in the f of x comma y. Otherwise, we may do another thing. What is that median filter? What is the median filter here? Take all the particular neighbor pixels of f of x comma y and then arrange that one in either in ascending or in descending. Then you just pick the middle value. Pick the middle value. That means here that is said to be here median filter. Okay, so if it is the odd values, and then take the center value as the desired pixel intensity. But if it is a even value, so right, if some case if I take the different mask, right, so then if the particular mask coefficients are even values, center pixel means here, so just take the two values, right, two center pixels values. So here then average those two, then take the new value. Okay, right, take the new pixel intensity value. So understood? That means here if I take the 3x3 mask, so consider the here coefficients f of x comma y along with the neighbor pixels, right? F of x comma y with the neighbor pixel intensity values. So arrange that one in either in ascending or in descending, and then consider only the center value, middle value, and then that is placed in the f of x comma y. Right? If it is an even value, right? If I take the what is that even number of weighted coefficients, so then here even number of what is that pixels f of x comma y with the neighbor pixels, here those are here even. Then in such a case also arrange that one in either in ascending order or in descending order. But here it is very difficult to choose the middle value. So that's why here consider the two values, right, middle two values, and then take the average. Okay, right. So that is the thing here, median filter. So now here each one is having a certain own application, right? So own advantage. So here best known filter is the median filter. Replaces the value of the center pixel by the median of the intensity values in the neighborhood of that pixel, which is used to remove impulse or salt and pepper noise. So here impulse noise and salt and pepper noise, we will see that one later. So remember the words here, salt and pepper noise is removed and impulse noise also removed. And then here minimum filter and maximum filter is there. So one is used to remove the salt noise and one is used to remove the pepper noise. Okay, right. It's okay. Median represents the 50th percentile of a ranked set of numbers. That is what I said, one procedure is there. That is said to be here 50th percentile. And while 100th or 0th percentile results in the maximum filter, minimum filter respectively. Right? It's okay. Now, this is nothing but order statistics filters. Okay. So, now consider this one. This is the input image. If I want to remove this salt and pepper noise, so if I apply the averaging mask with the 3x3, see this here, I cannot remove the whole image, whole noise in this. Okay, right? So, here with this we are not actually satisfied. Am I correct? So, here if I apply the median filter here, see this here, if I apply the 3x3 median filter, so here the noise is removed. Okay, see this. Okay, right. So in this way, we can choose the filter here depending on particular image. Okay, right. So now here coming to the here, we will see the sharpening filter in the next video. Okay, thank you.